All right, recorded is rolling. So it is Tuesday, November 15th. We're about to do Kahoot on conceptual questions for momentum. Now, where you guys can follow the findings if you want to follow along. Remember, this page we were working on yesterday and last week. Right? We finished all these. You guys have all these in your notes. Printed on the opposite side are 20 conceptual questions, which are the questions that we're going to cover with this Kahoot. You guys remember that Thursday, there's going to be an in-class quiz. It's going to be open notes. So any notes that you took last week, any notes that you guys took yesterday, any notes you take today, anything you write in class tomorrow, you can use open notes. Right. So we're in a shelter in place right now. In the off chance that they send us outside, let's review this real fast. So if they send us, suppose they send us outside, if they send us to site A, we're gonna go out the store, hang a left. We're gonna walk all the way down out the doors, this way down here to the left. We're gonna go to the bus loop. My number is number 29. It's printed in the bus loop, just like line up in a straight line. I'll have gripping on a stick, and you guys can find gripping on a stick and line up at number 29. That's if they send us to site A. If they send us to site B, which is the football field, this is where they have us organized by subject. Okay, so since we're a science class, okay, we're going to start out the same evacuation type route. Hang a left, go out these doors, right? But then we're going to go all the way to the football field. We'll be entering on this map on the bottom left of this map. Okay, and then we're going to walk the full length of the field, and then all the science classes are on this corner of the field. Okay? So same thing. You'll have gripping on a stick. You guys can find me there. Okay, so you guys remember that? All right, but you guys ready for Kahoot? Okay. And everybody's got that paper. You can follow along with the conceptual questions. So flip the screen over. Okay. A lot of you guys are hopped on already. Okay, let me pause this recording and give you guys a few more seconds to hop on. All right, recording is resumed. Okay, and let's start these questions. Momentum is defined as what? Yeah, mass times velocity. There you go. So you guys know that momentum is mass times velocity, right?
Oh. Dr. Cox, thank you for your cooperation. At this time, we're concluding our drill. We are no longer in shelter place, and you may resume normal activity.
All right. Any question why it's not any of those other ones? Okay. Okay, you guys got that? Okay. All right. All right, so you guys know momentum is mass times velocity. All right, number 2, if the momentum of an object changes, but say mass stays the same, what's going on? All right, yeah, so some of these maybe a little bit too small time interval to, so I guess I had 10 seconds to get that. But okay, you guys know that momentum is mass times velocity. So if that's changing, but mass is staying the same, that means that velocity for sure is changing. Okay, so right away I know that the gold one is true, velocity is changing. But hang on a minute, if velocity is changing, you guys know that there's an acceleration involved because the rate change of velocity is acceleration. So that means that the red one is also true, right? And if there's an acceleration, accelerations only happen if there's a what acting on it? A force, right? So force, so there must be a force acting on it, right? Actually, this red, blue, and yellow, if any one of those is true, all 3 have to be true. So all the above, okay? So impulse is change in momentum. All right, Zach picking up the points. Top spot. Table tennis ball launcher is fired compared to the force on the ball, the force on the launcher. Yeah, same force. All right, you guys remember that's Newton's third law of motion, isn't it? So it kind of goes back a few weeks. All right, so the force is the same. Now, really, that's a setup for this next question. Okay, so you guys know that the force is the same, right? Okay, so equal and opposite forces. All right, I'll look at all the points. We got Zach, Cole, Liam, Bella, and Evan getting points. So same scenario compared to the impulse on the ball, the impulse on the launcher. okay, would also be the same. And remember, the last question you guys just said that the force is the same, right? Right. And that force acts for the same time interval on both of them, right? Even if it's a variable force, like millisecond by millisecond, it'd be the same force per unit time. Unit time. So multiply this together, that's impulse, right? Force times time interval, right? Yeah, so the impulse is the same on both. Now it's opposite directions, but the magnitude is the same. Okay. But look what that means. That means also that the mass times change of velocity would be the same for both, wouldn't it? Right? Let me change out the scenario just a little bit. What if instead of a launcher and a ball, what if it's a cannon and a cannonball? Otherwise, it's basically the same idea, right? Cannon and a cannonball, right? So the impulse on the cannonball and the impulse on the cannon would also be the same magnitude, right? But doesn't the cannonball move off really fast, and the cannon itself probably recoils a little bit, but kind of moves back kind of slowly, right? Compared to the cannonball. Right? Now, why would that be? Because the cannon and the cannonball have very different what? Like masses, right? So even though it's the same impulse on both of them, same force, same time interval, same impulse, right? Different masses result in different velocity changes, right? Large mass, small velocity change, vice versa, right? Inverse relationship between mass and velocity change. Zach on fire, picking up more points. Collision is elastic if what? Oh, all right, nice. Yeah, those are all good, right? Now, if it's perfectly elastic, then definitely the gold one applies. Right? Kinetic energy is conserved. That's what I gave you guys definitionally. Right? If the objects don't stick together, is a pretty good choice because that's the opposite of inelastic. So okay, so that works too. Right? And then lasting deformation is also an example of inelastic. So if there's no lasting deformation, also be a clue that it would be elastic. So there you go. Those are all properties of elastic collisions. All right. Whoa, got points changed. We got Kaylani, Evan, Cole, Liam, and Zach still in the lead. Suppose standing on the pond, there's no friction between your feet and the ice. How do you get off the ice? Kind of reminds me of the Magic School Bus flip, right? Uh, yeah. All right, you have to throw something the other way, right? If you guys remember that Magic School Bus, yeah, let me see if I got it real fast. Might be able to pull this up. Uh, Here we go. Let me mute this so just so we can get the visual. Right. You guys remember on this frictionless field that once the kids were set in motion, like they were just going, right? The only way to get set in place is they had to be like external force. There's your external force, right? Putting all these kids in place, right? But then, see, I'm trying to run around here, right? They're all just well, okay. They're all stuck in place. Let me pull up part two of this. Part two. I don't think I showed this so much in class, but he hits this ball, and then that's what I wanted you guys to see. Right. Okay. It's Keisha playing third base, and she's just stuck. Right. She's trying to run towards the ball, but no luck. Right. Because there's nothing to push against because there's no friction. Okay. So the only way to move out of your spot is she'd have to like take her glove and like throw it, and then she'd get kicked back the other way. Okay. That's the only way. Right. Okay, you guys agree with that? Okay, so we're talking about like a perfectly frictionless scenario. Textbook physics. I got Liam on fire. Zach's still in the lead. Freight train rolls along a track with considerable momentum. What if it had the same speed but twice the mass, like twice the cargo? What would its momentum be? Yeah, twice the momentum, right? So momentum is mass times velocity. So if you double the mass, you double the total momentum. Right? Or if you left the mass the same and you double the velocity instead, that would also be double the momentum. Because what would happen if you double both the mass and the velocity? What would happen to the momentum? Yeah, that would be quadruple, right? That would be 4 times. Right, but if you only double one of those, okay. Then okay. So you guys give that. We got Evan on fire, Lynn in second, second first. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because. Yeah, there you go. The cannon has so much mass. Yeah, all right. Definitely glad you guys got that because we just talked about that, right? See, the force in the cannon and cannonball is the same, so the red one's no good. The impulse is also the same on the cannon as the cannonball. Right? The yellow one's not even true. So yeah, the green one is definitely the best answer. The cannon has so much mass, so much inertia that even with a really pretty good impulse, the change of velocity is going to be pretty small. In order to catch a ball, a baseball player moves his hand backward in the direction of the ball's motion. Doing this does reduce the force of impact. Why? Ooh, okay. That was pretty tricky. Somebody got it. Ooh, I'm curious to see who got it, but let me switch my screen over because a few of these I want to draw out on paper, including this one. So you got a glove, right? And here comes a ball, right? Move it in real fast. Okay. And you guys know that this ball has a mass and a velocity. Let's say altogether it comes out to like it's gonna make up a number. Let's say like 12 units of momentum, 12 kilogram meter per second. Okay. See, this is before picture. Okay. You guys see this like a glove going on right here, right? Okay. And then let's have an after picture. So we got the glove again. Okay. But now the ball's okay, comes to a dead stop right there. Okay, so we went to 0 kilogram meter per second. Okay. Okay. Now, if we're looking at the system of only the ball, then that is definitely an open system because there's an external force that's causing its momentum to change, right, from 12 to 0. Right, so the force is coming from the glove. Okay, how much is that force? This is like before, after. You guys see that? Before, after. Okay. Right, so how much force are we talking about? Well, you guys have an impulse formula that says that force times time interval is equal to mass times change in velocity. Okay. It's really an average force we're talking about, but you guys get the idea, right? You guys remember that? Okay. So you guys remember this impulse equation? You know, if you look at the poster, it's hanging above my ceiling. It's the poster that looks a lot like this guy right here. Now this is a graphical version, but if you have force versus time, it's the area under that curve. Okay. If it's a constant force, it give you like a rectangle type shape. If it's a variable force, it's just the area under the curve. But here you go. Here's a set, right? So the change in momentum, mass and change in velocity, okay, results from a force times some time interval. Okay, everything. Okay, so the change in momentum of the ball, the impulse on the ball, is the same regardless of how you catch it. If you just hold your glove still and you bam, just stop it all at once, be like, wow, that really stung my hand. That was a really huge force on my hand. But you went from 12 to 0 units of momentum from the baseball. If you pull your glove back while you're catching it, like, ooh, it wasn't as much force of impact. It didn't sting my hand as much. But the impulse of the ball is still the same. Mass change of velocity is still the same. It's still like 12 units. Okay. So something over here is changing. Okay. Now, definitely, if you pull your hand back, you can feel the force going down. But why? Well, it's because you're extending the time interval of that collision. Right. The time interval is going up. Right. Here, let's run some example numbers. Break out the pinky here. Let's do, like, you guys know this is all going to come to 12 because 12 to 0, the difference is like 12, right? 12, negative 12, everything. Right. What if you stop the ball in like 1 second? 1 second. How much force do you need? It's going to be 12 newtons, right? 12 newtons of force times 1 second is 12 kilogram meter per second. 12 newton second and kilogram meter per second is the same unit. Okay. But what if you pull your hand back while you're catching it and you double the amount of time this lasts for? What if you double it to 2 seconds? Now, how much force? What's the average force? 6. Oh, whoops, newtons. 6 newtons. Right? You guys see that the force got cut in half by doubling the time period? Okay. What if you tripled the initial time period to like 3 seconds? Now what's the force? Exactly. Now we're down to 4 newtons. Now it's a third of the original force by tripling the time, right? So there's an inverse relationship between these two guys, right? The more you extend the time interval, right, the less the average force. Okay. Okay, so you guys hear that? This concept is going to come up later. There's a question that involves like an apple falling from a tree and hitting the ground, and like what's the force of impact. So think about this one because I have a little bit more to say, but we'll save that question. It's coming up. And so back over to this Kahoot. Let's see who got this one right. Who got this one right? It's a pretty tricky question. Oh, Kaylani. Kaylani, get some points. Car traveling along the highway needs a certain amount of force to come to a stop, like braking force. More force would be required when the car has what? Yeah, those could all be examples of being the case, right? So if the car's more massive, it has more momentum to start, so you need more impulse to bring it to stop, so that'd be more force, right? Okay, if it has more momentum, you have a greater change in momentum to bring it to a stop, so you need more force times time interval. Okay, less stopping distance. There's a few different ways to think about this. One way to think about it is if it's less stopping distance, that's a shorter stopping time. And just like catching the baseball, if you shorten the time interval, you also need more force. Okay. Yeah, those are all true. All true. All right. Ooh. So we got Kaylani and Cole and Liam. Evan moved up to second, and Zach still holding on to the top spot. Here we go. Here's the apple hitting the ground. What does that actually depend on? All right, all the above. Those are all true. Okay. Now, this way I definitely want to switch over and talk a little bit more about the athletic hitting ground. Okay. This is one of my favorite physics questions here. So let's take a look at this apple. Okay. So here's this apple. It's like falling from a tree. Okay. And somewhere down here is the ground. Okay. And what's the force of that apple hitting on the ground? Okay. Well, I can tell you that's going to be more than the weight of the apple. Suppose the apple weight here, I'm going to do just some simplified crazy number. But what if the apple has a mass of 1 kilogram so that it weighs 10 newtons? Right? If there's a scale down, which is more than an apple would realistically weigh, but you guys get the idea. Just simple numbers. Okay. Suppose there's a scale down here, and the apple like lands on the scale. I can tell you that the scale is going to read more than those 10 newtons that it actually weighs. Right? So how much does it read? Well, I could say if I just simplify this a little bit to just average force, right, which is the maximum force might even be more than that, but the average force times the time interval of the collision, right? We're talking about probably a tiny fraction of a second. Is what the time interval is, delta t. Okay? Is the mass of the apple times its change in velocity. Okay. So F delta t is m delta v. There's your impulse equation, right? Okay. So what if the apple is like landing at again, simple numbers like 10 meters per second. Okay. And what if the apple just goes splat and it's perfectly inelastic? Okay. Well, I could say, let's plug in some numbers here. Say I got a 1 kilogram apple, for example, and it goes from 10 to 0 meters per second. That'd be a change in 10 meters, but actually be negative, but just keep it. You guys get the idea. Okay, meters per second. Okay. Let's say that the time interval is like 0.1 seconds. Okay. How much force would we need? Well, 10 times 1 divided by 0.1, that looks like 100 newtons. Okay, something like that, just example numbers. You guys get the idea? I think that works out, right? Okay. Now, one of the things you could change was the speed of the apple falls. So what if you like double the speed to like 20 meters per second that it's falling? Okay. So keep the mass of the apple the same. Let's say it's even the same time interval of falling. Okay. Well, the fact that you doubled the delta v means that the force is also going to increase by the exact same proportion. Right? Okay, so that's one thing you could change. Right? Maybe the apple fell from a higher distance, so its speed would be increasing. Okay? If you change the mass or the weight of the apple, it's going to be a very similar story. It will also be greater force of impact. Okay? Another answer choice was if you change the time interval. Okay? Okay, so here's how you can change the time interval, and it kind of goes back to the example of the glove catching the ball. Okay? Did I give you guys the example of like if you jump out a 3-story window? Did I give you guys that example? Suppose you're in a burning building, right, and you're on the 3rd floor. You have no choice but to jump out the window. Okay? Would you rather land on bam hard concrete or on a trampoline and warm? What sounds better? we're gonna land on a trampoline. Okay? And the physics of that is, well, your delta V doesn't change because you're falling some distance, so you're gonna land at some like whatever crash speed you're in. Okay? Your mass doesn't change, that didn't change. Okay. But if you can extend the time interval, so let's go back to the original example and knock this one out. Okay. So let's say you're falling, it's like 10 meters per second. You got 1 kilogram apple. Okay. If you can extend that time interval to, let's say like 10 times as much, just to be all crazy, take it to like a full second. You guys see that now we're down to like the 10th of the original force. You guys see that? Okay. Guys, inverse relationship between those two. Yeah, if you extend the time interval, you get less force. Okay. Would you rather land on concrete or carpet? Rather land on carpet. Same reason, right? Same idea. Okay. And there's one last multiple choice answer they did. They said, what if the apple, instead of going splat, what if the apple boing bounces off? And just to make up an example number, suppose it bounces off at like 8 meters per second. Okay. Now here's where you have to be kind of careful with this. Okay. Who can tell me what is the change in the velocity of the apple down 10 versus up 8? The change in velocity, and it's not 2 meters per second. What is it? What's the difference between 8 up and 10 down? 18. Yeah. No, you say 18. You guys say 18, right? Because isn't delta V equal to 8 meters per second minus negative 10 meters per second? These are vector values. Direction matters. That'd be 18 meters per second. Okay. So here, scratch this guy out too. Okay. Here, I've got my first example of then comparing everything to. Okay. So what if your delta V now like almost doubles? It could if this was a really elastic collision of the high coefficient of restitution. So what if we're up to 18 meters per second for this 1 kilogram apple? Okay, and let's keep the time interval the same. Here, I'll run the numbers real fast to see what this comes out to. Okay. So 18 times 1 divided by 1. Right. Look at 180 newtons of force. So comparing the first example to the last example where it bounces, here's where it sticks, here's where it bounces. You guys see a much greater force, like almost double the force by bouncing compared to sticking. Right? Does that kind of remind you guys? Remember, was it yesterday? Did I show you guys this example of you throw something in a bowling ball? If you throw the putty, it sticks. Then however much momentum the putty had all goes into the bowling ball plus putty system that rolls off with that much momentum. But if you throw a bouncy ball, the boing bounces off. You guys see like 3 minus -5 would be 8 units of momentum, right? Which is actually more momentum that's transferred into the ball, right? There's more impulse going on with the bounce ball situation, right? So same thing if the apple boing bounces off the scale is going to be the higher force value. All right, so a lot going on with that one. One of my favorite momentum questions going on right there. All right, next question. Or well, you got points. All right, so Zach's still in the lead, packing up some points. You guys did good with that one. Moving freight car runs into identical car at rest on the track, same mass. The cars coupled together. Compared to the velocity of the first car before the collision, the velocity of the combined cars after the collision is what? One winner. Okay. Why would it be half as much? Half as much. All right. So let's bring this back over here. Okay. Let me draw this out for you guys. Okay. So I got some railroad tracks. Draw some railroad tracks going on. Okay. I have one railroad car just sitting here, just minding his own business, and another railroad car. They said identical, so if you ever open a physics book that says identical, probably identical math is an important detail, right? Okay. And it's coming in at some velocity, so it's like. Okay. I'm just gonna make up some numbers. Let's say this guy has a mass of 1,000 kilograms, and this guy, of course, would have the same mass because it's identical. Okay. Now this guy's just at rest, right, which is providing no momentum to the system, right? Because 0 velocity, 0 momentum. Okay. But this guy, let's say, is coming in at V equals let's say 10 meters per second. Okay. So here's the framework that I'm using to solve this. Sum of momentum initial equals sum of momentum final. Okay, isn't that the setup for like so many problems in the last week? Okay. And all the momentum is being provided by the moving one, because it'd be mass. Here, throw one more step here in terms of variables. Mass times velocity equals the combined mass m plus m, because they're the same mass, so m plus m times v final. Okay, and the question is, what is the speed final compared to the speed initial? It should be half. But let's run the numbers and see if that's the case. So got 1,000 kilograms of mass moving at 10 meters per second. Okay. I could say plus 0, but whatever. This guy's not moving. Then the combined mass, 1,000 plus 1,000, isn't that like 2,000 kilograms combined mass times V final? If you solve for V final, well, 10 divided by 2, is that like 5 meters per second is V final? Okay. Okay. So if they couple together perfectly inelastic, that's what that is, right? Inelastic collision. Okay. 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 That's good. Switch back over here. Who picked up those points? Oh, Evan on fire. Zach's still in the lead. Piece of putty moving with 2 units of momentum strikes and sticks to heavy bowling ball initially at rest. The putty sticks to the ball. Both are set into motion with the combined momentum of what? Yeah, 2 units. Oh, nobody got that. All right. So this is just straight up conservation of momentum, right? Okay. This is a perfectly inelastic collision. The momentum before the collision is equal to the momentum after the collision. Yeah, 2 units of momentum. Right. Now the velocity might be really small. Right. They might be rolling off really slowly because the bowling ball is so massive. But if you do the combined mass times that very small velocity, it's still 2 units of momentum. Okay. You guys get that? Any questions? Why that's the case? All right. So here's the follow-up question: is what if you just change it with the bouncy ball? That the bowling bounces off the bowling ball. Then the bowling ball itself is set into motion with the momentum of what? Yeah. In that case, it would be actually more than 2 units. Okay. I was saying with the apple bouncing off the scale, it'd be there would be a greater force due to bouncing. Okay, so similar thought process going on here. Let me draw these out for you guys. Okay. So the top of the half of the paper is the last question, and then the bottom half of the paper would be the question we just did. Okay. So if you have a bowling ball and a piece of putty coming in that sticks to the bowling ball, okay. If it was coming in with 2 kilogram meter per second, then after the collision, bam, you still got 2 kilogram meter per second combined momentum. Okay. But new scenario, if you have a bouncy ball, the boing bounces off. Suppose it's coming in with like 2 kilograms meter per second, and it rebounds with 1 kilogram meter per second, multiplying mass times velocity of the bouncy ball, right? Boing. Okay. Okay, now here's where you have to take the change in direction into account. The fact that the boing bounces off. Okay, so what is 1 to the left and 2 to the right? What's the difference between 1 to the left and 2 to the right? 3. 3 units, right? Let me draw a number line. You guys for sure get this. If you have 1 to the left and 2 units to the right, you guys see that change right there? It's going to be 3 units. 3 units. Okay. So how much momentum does the bowling ball roll off with? 3 kilogram meter per second. Okay. Because change in 3 units of moment, the impulse of -3 units for the bouncy ball, same impulse on the bowling ball, +3. Well, opposite sign, but same impulse, right? Okay, so 3 units of momentum. Right? The bowling ball actually rolls off faster by the bouncy ball rolling off it. All right, got Kaylani and Zach picking up the points. The force that accelerates a rocket into outer space is exerted on the rocket by what? Where's that force coming from? Yeah, exhaust gases. Right, so we see a rocket launch into space. Right, you guys seen plenty of rockets, right? You're here in Brevard County, Space Coast. So what's propelling it up? Well, there's some rocket fuel, right? I think NASA uses hydrogen, and some of the private companies, SpaceX, use like methane for the most part. But there's some kind of combustion going on. Okay? And then this could be a dynamics question, Newton's third law of motion, right? Equal and opposite forces. Or this could be an impulse question, right? Mass times velocity of the rocket going up equals mass times velocity of the that rocket fuel being combusted going the other way. Yeah, exhaust gases. Equal and opposite forces, equal and opposite momentum. Up it goes. Cannon shot from a long barrel cannon travels faster than one from a short barrel cannon. True. Why? Because the long barrel cannonball receives a greater what? Got one winner there. There's a little tricky thing about that. I think you guys can get those. Right. The magnitude of force might actually be the same or pretty close, right? But if it's a long barrel cannon, that force acts for a longer time interval. And you guys know that force times time interval is impulse. That's going to translate into mass times change of velocity. So even for the same mass cannonball, you have end up with a greater change of velocity. Okay, you guys get that? Okay. So I've got long barrel cannon. The force acts for a longer time interval, more impulse, greater change of velocity. All right, Liam, getting the points. 2 kilogram ball thrown at 3 meters per second. What's the momentum? Yeah, there you go. Mass times velocity. Okay, so 6 kilogram meter per second. All right, we get some points. All right, Liam on fire, second spot. Zach in first. What if you have a 4 kilogram ball with a momentum of 20 kilogram meter per second? What is its speed? Oh, nice. Yeah, my last class missed this, so I'm glad you guys got that. Okay. So you guys took the momentum and divided by the mass. That would give you the velocity, right? The speed. 20 divided by 4 is 5. All right. And one more of these type basic calculations. Liam on fire, Zach still in first. Suppose it's moving 6 meters per second and has a momentum of 24 kilogram meter per second. What is the ball's mass? So did you guys take 24? Yeah, 24 units of momentum divided by 6 meters per second, and you guys got 4 kilograms, right? Or if you work back from the answer, 4 kilograms times 6 meters per second gives you 24 kilogram meter per second worth of momentum. Okay, guess that. Okay. Any question on those last three? Okay. All right. There's a question somewhere in here that's actually not on your page. I think it might be this next one. Let's say. Yeah, okay, this is not on your page, but while roller skating, Granny collides with her tiny grandson, Ambrose, who is at rest. Ignoring any friction effects, Ambrose's speed after the collision will be greatest. Where we send Ambrose off, flying off the fastest? When they collide together, or when they boing bounce off each other? Which one's going to send the little kid flying off the fastest? Yeah, that bouncing collision, right? So when you boing bounce off, there's a greater impulse, there's a greater average force, there's greater change of momentum, greater final velocity. There you go. And also more of the kinetic energy is conserved. Right. Any questions on that? Great. This is a lot like that apple falling question. This is a lot like the catching the baseball question. This is like falling on a trampoline question. Right. They're all related to each other. Okay. All right, we got Liam on fire in second, Zach top spot, and last question right here for the win. If all people, animals, trains, trucks all over the world began to run or walk towards the east, you guys know the world already spins towards the east, right? So what if everything on the surface started going that way? What would the earth underneath do? Ooh, all right. Here, let's flip the screen over. So this one takes some thinking, but flip it on the computer here too. There we go. Okay. So here's the Earth. This was more like a rotational momentum type question, which I think we're gonna have to push off to January, but we're gonna do a whole section on rotational dynamics. Right, so everything you guys learned so far, like in a linear sense, is gonna come back to rotation. But here's an example of that. So here's the Earth, North Pole, South Pole. The Earth, you guys know, rotates west to east like this. Right, so this, is that right? Okay. Now the Earth is like a closed system, right? The Earth itself and all the, everything on its surface, right? What if you sort of separated those two? You take everything on the surface, all these trains and people and animals and right? They all start walking towards the east. Okay. Now you could think of this in terms of forces, because aren't they like pushing back beneath the ground beneath them the other way? Is that like slowing the Earth down? Right. Or if you thought about conservation of angular momentum, which is kind of what we're doing with conservation of momentum, just in a rotational sense, you get the same result, right? If everything on the surface starts going even faster to the right, then everything below it has to respond by slowing down a little bit, get kicked back the other way a little bit. Right? Now, that's not a permanent change. As soon as like all the people and trains and animals come to a stop, then the Earth spin just gets restored to its original speed. So nothing changes in the net. All right, so back over here. Let's see our winners. The podium with the bronze, Evan. With the silver, Liam. And the gold, Zach. All right, count that too. Runners up, got Kaylani and Cole. All right, nice job, guys. Nice job. All right, so let me switch back over here. Do we have a? All right, so we have a few minutes. Okay, here's what I do. Let me pull some questions out of here. Or wait, does anybody have any questions about anything so far? Anything so far? Okay, so just to remind you guys, the quiz on Thursday, tomorrow's going to be a review type day. I'll give you guys another page that looks like this, just the numbers will be different. And so you guys get a little bit more practice and a final chance to ask me any questions tomorrow. Right? And then your actual quiz on Thursday, some of the questions are going to come from this paper. Again, just the numbers will be different. Okay? The scenarios will be the same. Some of the questions will be the conceptual questions that we just covered. So you guys just got all these answers, right? It's about half. Right? I pull some questions out here though. Actually, we just did that. Let's do Jocko the Clown. Okay. Actually, here, this will be the last question of the day, but we'll conclude on Jocko the Clown. Right, Jocko has a mass of 60 kilograms. He stands at rest on ice. Ooh, that's like that magic school bus baseball field, right? So there's zero friction, right? Right. And then somebody throws a 20-kilogram ball at him, right? Extremely heavy ball, but let's just run with it. Okay. And it's going at him at 10 kilometers per hour. Ooh, a little bit different unit, kilometers per hour. But we can build that. How fast do they move together across the ice? I'll solve it. You guys solve it. I forget what the answer is, but we'll get it all together. How about that? Okay. When somebody gets the answer, raise your hand. How fast? So start to solve it. See if you guys can beat each of the answer. So the framework is momentum is conserved. Right? Maybe like that. Okay. Actually, guys, what kind of collision is this? This is perfectly lit. Inelastic, right? Inelastic. Okay. So we got the mass of the ball times velocity of the ball. Isn't that the source of all the momentum in the system? That's pre-collision. Okay. So this is initial, final, pre-collision, post-collision. After the collision, isn't it the mass of the ball plus mass of Jocko times the speed together? I'll call it VI. Okay. And which is what we're solving for. Right? Is that true? Okay. So see, the ball was 20 kilograms. So you got 20 kg moving at 10. Let's do kilometers per hour. Kilometers per hour. Okay. I want to say that's about 6 miles an hour, I think, something like that. Okay. Okay. And then the combined mass. Well, let's just go ahead and take care of that. Couldn't that be 80? Right, 60 plus 20 is 80. Is that true? It's 80 kilogram combined mass. Okay. Okay. So who sees it now? What's the combined velocity? How about you? Okay. Okay. So one algebra step. Can you divide this mass down? Okay. Guess what is 20 divided by 80? That's like a quarter, right? And then the kilograms cancel. Kg, whatever that cancels. Okay. Times the original 10 kilometers per hour. It's VF. So the fact that the mass effectively like quadrupled means that we have a quarter, because this right here is 1/4, right? 1/4 of the original 10 kilometers an hour. Right? So okay, now you guys see it, right? What's the answer? Feel like 2.5 kilometers per hour. Somewhere about that. Okay, let's double check, make sure that's the answer. Yeah, 2.5 kilometers per hour. Here you go. Hey, look, that's the long barrel cannon. Okay. For the same force, why is the speed from a longer cannon faster? Well, should be because it has a greater time interval, so greater impulse. All right, so let's close class right there. Tomorrow, you guys have a chance to get some more practice problems and ask me any questions leading into the in-class quiz on Thursday.